Alright, so today we reached to week 3, day 1. So we will start linear regression. Before we continue with linear regression, let's review a little bit about correlation. Okay, let's go into a little bit detail. So we will talk about what is correlation again and what are the properties. Okay. Okay, so let's look at this data. This data is from U.S. United States in 2010. So they look at the percentage of high school graduate among the states, okay, of the United States, and also look at the percentage in poverty, and then they did a scatter plot. Okay, so you can see that this scatter plot pattern is decreasing. Okay, so based on this plot, we can say that the percentage of high school graduate has some linear association with the percentage in poverty. Okay, poverty percentage. So this data is coming from 50 states, so 51 states from United States of America. The poverty line, the percentage in poverty, the poverty line that cut off the percentage is the income below 23,000 per year, annual income for a family of 4 in 2012. Okay, so what is the response variable? So basically, there is no proper response explanatory variable, but we can think, okay, which one caused which. So we can think the logical pathway for high school graduate, which represent education. Okay, so the percentage of educated people may well reflect the percentage of the poverty. Okay, so probably the response, okay, the outcome, we can say that is poverty percentage. And then what can we explain, what further can explain this poverty percentage? So this can be the high school graduate, okay? And then we can say that, okay, this could be some kind of relationship here, okay? Downward direction. So we can say that, okay, this could be linear, and this could be, which is the inverse relationship, so it is negative. And we can say that, okay, a little bit strong, right? So we can see the pattern here. So it is based on the scatter plot. So we already talked about correlation in week 2. But here we will talk a little bit more, okay? So the correlation describes the strength of the linear association between two variables, okay? So correlation is the linear association. Assess the linear association. And we denote this correlation as R, okay? So correlation is as capital R or small I. It's no difference. It's not different. Okay, so what are the properties of correlation? Okay, so the property is the magnitude. Okay, the first one is the magnitude of the correlation coefficient, measure the strength of association. Okay, so by looking at the correlation, we know that the strength of the linear association between two numerical variables. Okay, so the first property is the strength of linear. We can assess the strength of linear association between two numerical variables. So you can look at these 3 figures. The first one indicated, okay, so the first one is a very nice positive upward relationship, okay, between X and Y. And the second, okay, so look at this Look at this, okay? So it is quite, quite dense in the middle. And even if you draw a straight line, you can perfectly fit this, okay? So it's, you can see that the variability is not, it's quite narrow, and it falls quite nicely along the line. So we can say that this is very strong association, okay, between two variables. This is the positive association, but this is the property one. So we'll talk about the strength or linear association. So if you look at the second group, second picture, and the same, we can draw this one, but you can see that the scattering and the point are more scattered than the first plot. Okay, so we can say that, okay, this there is, I mean, there is still the upward pattern, but the scattering is a little big. So we can say that, okay, this is fairly strong association. Okay, moderate association. Okay, the last picture, the last figure, which show almost no pattern. Okay, so it shows like that, and then the scattering is quite, big. It's scattered all over the plot. Okay, so these three plots, if we look at the correlation coefficient, you can see that this the first correlation coefficient of the first plot is almost 1. Okay, so because it is the upward, so it is positive, so almost 1. And the second is around 5.5. Okay, and the last one is almost close to 0. Okay, 0.07 is almost close to 0. So there is no association in the last plot. Okay, so the first property is by looking at the correlation coefficient, we know the strength of the linear association. Okay, and the second property, we know the duration. Okay, duration. So if you look at this, the first plot show the positive association. Okay, very strong positive association, and the second plot indicate very strong but negative downward association. Okay, so second property indicates the duration of association. Okay, what about the next one? I think we already discussed this, but let's review them. Okay, correlation coefficient is always between -1 and +1. Okay, we already talked about this. -1, what is -1? It is perfect negative linear association. Okay, so that is the word linear. Correlation is always linear. Assess the linear association. Okay, so even when you get a result, say R is equal to close to 0, and we could say that there is no linear association. Okay, we cannot say that there is no association because correlation assess the linear association. So in that case, we have to look at the scatter plot, whether it shows any pattern like the exponential pattern. Okay, so if your plot looks like the exponential pattern, okay, if your data, the relationship between two variables is exponential, then you cannot fit into the correlation. Okay, it will give you fairly insignificant result. So anyway, you have to remember, okay, this point is important. Correlation coefficient assess the linear association, and it is always between -1 and +1. Okay, -1 indicate perfect linear, perfect association, negative association, and +1 indicate perfect positive linear association. And 0 mean basically no linear relationship. Okay, so always there is a linear term. Okay, here, so which is the perfect one? Upward and downward, and then 0. Okay. The next one is correlation coefficient is unitless. Okay, and there is no unit because it is a ratio. So it is the ratio of standard deviation of x and y. Okay, so it is basically unitless. and it is not affected by changes, something like if you convert the unit. Okay, so let's look at this plot. So this plot is from about the mammals. Okay, so on the x-axis we look at the body weight of mammals, and on the y-axis we look at the number of hours of sleep of mammals. So anyway, when we look at this one, the first plot is measuring kilogram, and the second plot is measuring in pound. So even if the unit has been changed, or if it is scaled, something like log transform, okay? Even if these data are transformed, the correlation will not change, okay? It will not affect the correlation. Okay, so without this label, it's fairly the same, okay? But the marks are different, okay? The scale are different on x-axis. So 5, correlation of X and Y is the same as Y and X, okay? So if you switch the axis, it will give you the same correlation. It doesn't matter, okay? So this is about the mammals, plotting the lifespan in years of mammal and the number of hours of sleep of these mammals. So the plot change, when you switch the axis, the plot change, okay, but it's only the same, okay? You just, make it 90 degree something. Okay, anyway, if you switch the axis, it does not, the correlation coefficient does not change. It will remain the same, okay? So another thing is, so what is correlation coefficient? How to calculate correlation coefficient? It is calculated by standard deviation, okay? Essentially by standard deviation. So it is sensitive to outliers, okay? Like we discussed in descriptive statistics. So we got two plots with the same age scale, okay? On the exit, it goes from 0 to 50. On here, the same, 0 to 50. So these plots are, okay, why we made this? Because to compare, okay? So on the right plot, on the second plot, we have an outlier, okay? So for the first plot, it gives you a near perfect linear association, okay? Well, positive linear association. But when you have one single outlier, it drastically changes from decrease from strong, almost perfect linear to moderate association. Okay, so outliers are really important, and you need to explore your data if there is an outlier or not. Okay, anyway, that is the brief discussion of overview of correlation coefficient and the interpretation or the properties, you can say. And based on that discussion, we can answer this question, okay? Which of the following is the best guess for the correlation coefficient between poverty percentage and high school graduate percentage? So we got this scatter plot, the same scatter plot we see in slide number 1. And it gives you as a linear line, okay? Least square line. So we got A, okay. Okay, we got A 0.6 is quite quick. Response is quite quick. 0.6 minus 0.75. Okay, anyway, let's look at it. Let's look at this, okay? So we got a negative downward trend, okay? So this is negative. So we can eliminate the positive one, okay? It's quite easy, okay? So this is negative association, so we eliminate the positive one. Second, linear should be -1 to +1, okay? Linear correlation coefficient should be between -1 and +1. So this is false, okay? It's greater than -1. Okay, let's see. So we got minus 0.1 and minus 0.7, okay? So this is fairly scattered. along the line. So we could say that it's fairly moderate association. So we finally picked this one, okay? And then number B, okay, minus 0.75. Okay, well done. I mean, the response is quite quick. Okay, anyway, okay, so which one of the following has the strongest correlation? That is correlation coefficient closest to +1 or -1. What do you think? It should be pretty obvious, right? What do you think? Which one will be the strongest correlation? Yes, you're correct. Okay, B. Why not choose A? Why you don't choose A? Because it's even, you know, scatter, not quite condensed in the middle. Why not choose A? No response? Okay, anyway, so in plot A, we have we do not have a linear association. Okay, we have some curve pattern. So this is not linear association, so we do not choose A. Okay. Okay, well done. Not linear. Okay, next. Okay, we already know that. Okay, after linear, after association, the correlation coefficient, we should talk about the residual. Okay, I mean residual. What are residuals? Okay, so it is basically they are leftovers. Okay, leftovers from a model fit. Okay, understand this. Okay. What are the leftover? So in linear regression, what we always trying to do is we fit all these points, okay? So these, okay, green, let's call this green. Green point are the data, okay? So we want to fit, we want to give it a line that fit, I mean, that perfectly represent the relationship between high school graduate and the poverty. Okay, but we only want to fit it with a line, okay, because it is easy to understand, and mathematically we can make all sort of calculation if we have one line. Okay, so when we fit these data, I mean fit mean you draw a line, okay, you draw a line in the between these data, and then the distance between the line and the point is called the residual. Okay, basically that is so fit is, what is fit? Fit is on the point of the line. Okay, so these lines are drawn by by connecting lines. Okay, so here at the end of the yellow line there is a point. Okay, at the end of the yellow line there is a point, and so on. So we, based on the data, we make some prediction. Basically, it is like guessing. Okay, let's say guessing, and then put a point here, and put a point here, put a point here, and then we draw a line, straight line, connecting all these points. Okay. Anyway, so what is the residual? So the residual plus these data constitute our data. Okay, makes our data. So anyway, what is the residual? It is the difference between observed and predicted y. Okay, so in coming discussion, we will always refer our the response variable as y. Okay, y means our response variable. In this case, our poverty. Okay, so basically we observe y, and then we observe we predict y. So the difference between these observed and predicted y is called residual. Okay, right at this moment, do not confuse about the how to calculate these predicted y. Okay, Just remember the observed and the difference between observed and predicted y is called a residual. Okay, so basically to write this sentence in mathematical formula is this. Okay, so we call residual as EI. I represent the number of observation. Okay, so when you have 100, say 100 patients, then this I will go from 1 to 100. Okay, so what is E? E represent the error. Okay, so residual is the error we cannot explain. Okay, or the data cannot explain. So residual is the error. That's why we denote it with E. And then we have Y. Okay, Y is basically our response variable. Okay, or our outcome variable. So we have outcome variable here, and then they have the data from 1 to 100, say. And then we predict. So this comes later after we run linear regression. Okay. But anyway, the idea is when you put something like a hat, okay, something like a hat on the response variable, it becomes the predicted value, okay, or the estimated value. So we got the observed, which means it comes from our sample data, okay. So we got the observed and the predicted, and we subtract that, and we got the error or the residual. Okay, so basically this is the name of the states in United States. Okay, DC is Washington DC, and RI is Rhode Island. So as you can see that these are the two, farthest point from the line. Okay, so we put our knowledge here. So this blue point is our observed data, okay, data point. And then on the red, at the end of the yellow line, on the red line, we got our predicted value, okay, of predicted value of this Rhode Island, okay. So the difference between them is, as you can see, around 10.5 to 14.2. So we will say that around 4.16% less than predicted, okay. So the actual value is less than predicted value, okay. Or you can say that the predicted value is greater than the actual value, okay. Anyway, so let's see here. So the observed value is Washington DC, this blue point, and then the predicted value is here on the red line. And then the difference is called the residual, okay. Residual is around 5.44%. Okay, so if our predicted value is greater than the observed value, we call it an overestimation, okay, overestimate, our prediction overestimated. And if the predicted value is less than the observed value, then we call it an estimation, okay. Anyway, that is not that important, but that is all about the residual. And then we will talk about the least squares line, okay, least squares line. And then we will explain why does it mean to be a least squares line. And then we will talk about how to calculate slope and how to calculate intercept. Okay, so a measure for a baseline. So basically, we talk about the errors and we call it residual, okay? So one of the best line, okay, one of the best line on that scatter plot is to make the most minimal error, okay? We will choose the line with the least error or with the minimum error. And how to calculate this? We have two options. The first one is, okay, why don't we sum every error, okay? So say if you have 100 data point, okay, 100 data point, then you got 100 error residual, okay? residual values. So why don't we sum them and see which line will give us the lowest value here. That is one option. But the problem is, you see, here what we do is we subtract, based on this formula, we always subtract y with the predicted value. Okay, observe with the predicted value. So it will give us positive and negative. Okay, positive and negative, and it will give us, okay, wait, okay, anyway, when we subtract y with predicted y hat, it will give, so this one, it will give negative, okay, on this side, and on the above, on top side, it will give us positive value. Okay, so the problem with is, when we add them positive and negative value, it will cancel out each other. Okay, it will cancel each other out, and then we will have very small value. So we have option 2. Okay, why don't we square them? Okay, when we square them, the negative sign will disappear. Okay, so that is called sum or square residual. Okay, sum of square residual, and then we square and we sum them. Basically, we call this the least square. Okay, so we want the smallest number of this value. Okay, smallest value. So why least square? Because it is very easy to calculate. Okay, and then we can say that a residual which is twice as large as the other is more than twice as bad. Okay, so when we square them, the residual value will get bigger, and then we can see the effect twice as much. Okay, twice as bad. So at least we can say something by getting a larger value. Rather than having a smaller value if we add the residual without squaring them. Okay, anyway, so how do we define the least square line by mathematical formula? So this is the definition. Okay, so this is some textbooks give us something like this. Okay, a plus bx. Okay, I think this one is much more familiar with you. Okay, so beta 0 is the same as a, and beta 1 is the same as b. Okay, so if you want to understand linear regression in detail, then you need to go back to linear algebra and look at the equation and solve the equation, and then draw the graph and all these. So you will have a better understanding of the linear regression in detail. Okay, otherwise don't bother. So to simplify this complicated formula, we can write y is equal to a plus bx. Okay, what are a and b? These are called constants. Okay, but anyway, we have y hat. Okay, y hat, what is y hat? That is the predicted y. Okay, so how do we predict? We predict by beta 0 is called the intercept. Okay, we will explain what is intercept and what is slope, and then beta 1 is slope. So we predict by multiplying the so y is the response variable. Okay, x is the explanatory variable. Okay, so basically in our example, y is the poverty percentage and x is the high school graduate. So how do we find the predicted value? We multiply the high school graduate with the slope, and then add that sum with intercept value. Okay, and so this is how you find the least square line. Okay, anyway. Okay, so a little bit about the notation. When you talk about the beta 0 and beta 1, it talks about the parameter, okay? And then we only have the sample, so we have to work with the point estimate. But this is like the strict rule for mathematical expression, but we don't have to worry about that. We just need to understand 0 means intercept and 1 means slope, okay? Okay, so we know how to calculate the response variable, but how do we find the slope and how do we find the intercept? Okay, so to simplify this, okay, when we get to the earlier example, say this is our plot, okay, this is our scatter plot, and then what we have to do if we do not have this formula is we have to draw multiple line. Okay, we have to draw multiple line and see which line will give you the lowest number of the square, sum of square. Okay, so you have to draw many lines, thousands of lines to fit the data and see if which lines give you the least residual sum or residual number. Okay, so mathematicians, they came up with the using calculus, they came up with a formula. Finally, we can say that we can calculate slope by dividing standard deviation of y, which is the response variable, and standard deviation of x, which is the explanatory variable. Okay, and multiplying with correlation. Okay, so that is what they came up. Okay, so this is the R formula, right? Correlation of x and y, we get the correlation coefficient, and then we find the standard deviation of y divided by standard deviation of x and multiplying, and then we got the slope. Okay, so this is how they came up with the methods to calculate slope. Okay, let's see an example. So we got a standard deviation. Okay, standard deviation of percentage living poverty is 3.1%, and then standard deviation of high school graduate percentage is 3.73%. Okay, so living poverty is our response variable, high school graduates is our explanatory variable. We got the correlation between these two values is minus 0.75. Okay, so they want to know what is the slope. Okay, so we got a given data here, and then we can calculate this manually, but usually we don't do this. We just calculate it, we just use the software to get a coefficient value. Okay, but you can do that manually if you know this number, and then we can calculate by putting these numbers, and then we got approximately minus 0.62. Okay, so how to interpret this slope? Because this is rather important, okay, that we are dealing with linear regression. So in linear regression, the interpretation of slope is for each percentage point increase. Okay, this one is based on this context. Okay, so let's interpret this in this US example. For each percentage point increase in high school graduate, we will expect the percentage of living in poverty to be lower on average by 0.62 percentage point. Okay, so basically, one unit increase in explanatory variable, the response variable will decrease by 0.2 unit. Okay, so that is essentially because we have a negative association, and we can confirm this by correlation, right? Because correlation coefficient give us two things, and two properties. The first one is the direction, and the second one is the strength of the association. But by using linear regression, we can quantify this association, okay, by using this slope, okay. So how much this will decrease if we increase 1 unit, okay. So this is essentially how we interpret the slope value. So you look at the sign, or the direction. So if it is plus, then both sides will increase, okay? Both explanatory and response variable will increase. If it is minus, then one increase and one decrease. Okay, so let's look at this. The regression model for predicting length of gestation in days from lifespan for mammals in years has a slope of 0.08. Which of the following is the best interpretation of this slope? Okay, so why don't we just give a number? So we will say that it is A, it is B, it is C, and it is D. Okay, so for each additional year lifespan, gestation is better to be higher on average by 0.08 days. And then each additional year lifespan increases gestation by 0.08 days, and so on. Okay, so which one do you think is the best interpretation? A, B, C, D. Which one is the best interpretation? Are you sure? Okay, wait. So one respond that this should be A, right? And another one respond, this should be C. Okay, so first you need to think about which one is explanatory variable and which one is response variable. Okay, so time is almost up. So why don't we stop this, and then I will restart the meeting. Okay, so you just take a moment and okay, so all right. Yes, correct, A. Okay, so before we continue this problem, you need to understand which is explanatory variable and which one is response variable. Okay, so you just have to think logically. Sometimes it's not the context is not given. So the regression model for predicting the length of gestation and the lifespan. Okay, so we look at the lifespan and we look at the gestation. Okay, anyway, based on the lifespan, okay, we predict length of gestation. So which means that, so it has the word predict, right? So this one should be explanatory response variable, okay? Because we say that predicting this variable. So this is the response variable. How do we predict? We predict based on the lifespan, okay, from the lifespan. So this one is the explanatory variable. And then it said it has a slope of 0.08. So the interpretation is for each additional year of lifespan. Okay, so we have to, if we give it 1 unit increase in lifespan, we have this one is positive association. Okay, so the length of gestation will go up 0.08 unit. Okay, so for each additional year of lifespan, gestation is better to be higher on average by 0.08 days. Okay, so this one is the correct answer, the first one. So what is the difference? The difference is the association and the causation. Okay, so in this statement, we only say that gestation is expected to be higher. Here, it says that each additional year of lifespan increases. So it says it caused the gestation. Okay, but by association or by the slope, we cannot say anything about causation. Okay, we are not talking about any causation. We only say that there is a relationship and the quantity of the relationship is 0.08. So we cannot say this cause that. Okay, X cause Y. We cannot say that by linear regression. Okay, we can only say there is association. So that is the difference. And the other one is the response and the explanatory variable is wrong. Okay, so the correct answer is the first one. Okay, let us move on. Okay, so far we have calculated slope. What about the intercept? So basically, the intercept is the intercept of the least square lines always go through the mean of X and Y. Okay, so we can use based on this fact. So we have the formula y predicted the predicted y is equal to the intercept plus slope, and then multiply with the explanatory variable, and then we replace this y with the mean of y and x with the mean of x. Okay, and then we change it so that we get the intercept. Okay, so what is the intercept? Intercept is basically we subtract the mean of y, okay, the mean of y with the multiplication of mean of x and the slope. Okay. Okay, so I think the intercept is one. The intercept. What is the intercept? Okay. Intercept is the value of y, the value of predicted y when x is 0. Okay. Basically, if when x is 0, when you put 0 in a place of x, this plus b1 x will become 0. Okay, so essentially when x becomes 0, so you look at the x AZ and look at the far right side, and then you will see there's 0. Okay, so if it is 0, where would y be? Okay, so basically it's the start of this one. But here, you just have to understand whether it is meaningful, okay, to have the 0 in this high school graduate. Okay, should there be a 0% of 0 proportion of high school graduate in United States? No, it's not meaningful, right? So usually we don't interpret intercept. We usually use slope and interpret the result of slope. Okay, but we usually use intercept to make the prediction, to make the predicted y value. Okay, anyway, this is the intercept. Okay, what is the intercept? Intercept is the value. Intercept is the value of predicted y when x becomes 0. Okay. Okay, so let's take a look at this example again. So given that the average living poverty is this, okay, we got the mean, and then we got the intercept. Okay, we find the intercept. So we plug in the value to the formula, and then we got intercept value of 64.68. Okay, so how do we interpret this? We interpret, okay, basically state with no high school graduates, okay, are expected on average to have a 64.68% of their poverty line. Okay. Okay, so basically there shouldn't be no 0 in this HS because 0 does not have any meaning, but probably this could be, I don't know, maybe this cannot be true in country around the world these days. No high school graduate, or probably there is. So anyway, when we look at the intercept, we calculate intercept by using means. Okay, And then we calculate slope by using standard deviation and correlation coefficient. Okay, that is the difference. And now let's put it in our formula, final formula. Okay, so the final formula is our predicted percentage in poverty. How do we predict? We predict by using this formula. Okay, the intercept is 64.68 minus the slope is 0.62 multiplied with the percentage or high school graduate. Okay, so you will get this least square line. So anyway, in R you will get this table. Okay, when we calculate R, we got an estimate. Okay, which is the intercept, this value, and the slope, which represent the explanatory constant for the explanatory variable. Okay. Okay, so in order to recap, intercept is basically 1/8 is equal to 0. That is the value of the that is the value of y. Okay, or predator y. Okay, so we just want to draw the line, but sometimes it is meaningful. Sometimes it is meaningless. Okay. Something like age, when you normally don't have age 0. Okay. Like sometimes in the it does not have any, it does not convey any meaning. So we usually do not interpret intercept, but slope we have to interpret it. It is the most important. I mean, it is the value that quantifying the relationship between two numerical variables. So it is what we want to find in linear relationship, in linear regression. Okay, so how do we interpret slope? So basically, intercept is where the line starts. Okay, and then what is the slope? The slope is how much the line goes upward or downward if the unit increase. Okay, if there is an increase in unit. So basically, for each unit in increase in x, y is better to be higher or lower on average. Okay. So based on the direction, okay, if it is a positive relationship, if one is if one, we increase 1 unit, and then the y will also increase by the slope. Okay, and when x increase 1 unit, for a negative relationship, the y decrease by the slope. Okay, so I think today we talk about correlation, and then we discuss what is residual. Basically, residuals are errors, which are basically the difference between observed value of y and the predicted value of y. Okay, normally we didn't have that when we get our data. So we only get the line after we fit into the linear regression. Okay, so this is the residual. So residual are the residuals are something that is not explained by the data. And then we talk about the least square. Okay, why we use the least square in this case? If we do not have the linear formula, which is y is equal to beta 0 plus beta 1/8, then we would have to draw thousands of lines, okay, multiple lines to fit our data and calculate everything by hand. Okay, so they come up with using calculus, they come up with a formula. The final formula is to calculate slope and intercept. Okay, how do we calculate slope? Slope is basically coming from standard deviation of x and y and multiplying with the correlation coefficient. Okay, that is why the correlation coefficient is important to linear regression. And we talked about how to calculate the intercept. Okay, basically intercept is the start of the line, and then one is or the explanatory value. There is no explanatory value, and that would be the value of predicted y or y value. And then finally, we usually we do not interpret intercept, and the main value we look for is the slope. Okay, I think that is for today, and tomorrow we will look at the we will look at how to fit linear regression in R and interpret the result. Okay, so basically that is the start of linear regression. Okay, that is not the end. Otherwise, okay, there is a lot we have to do to use the linear regression. Okay, so anyway, first thing tomorrow, we will fit linear regression. Okay, using our data set and everything, and then trying to interpret the value, the slope in our context, and then trying to look at the confidence interval and the p-value. Okay, which we have discussed in length in week 2. Okay, and then what we will do tomorrow is only looking at the association of between two numerical variables. Okay. Okay, I think at this point, if you are not clear, let me repeat this. So when do we use linear regression? Okay, if you have if your response variable or your outcome, okay, your outcome of the study is numerical data. Okay, what numerical data? It is continuous numerical data. Okay, if your outcome data is continuous numerical data, you use linear regression. You can use linear regression. There are other modeling methods you can use. Okay, so anyway, I think the idea here is first we will look at simple. Okay, we will look at simply by looking at two numerical variables. And then we look at how we interpret by looking at when our outcome is continuous numerical variable and our explanatory variable is categorical variable. Okay, and then we will go on with the conditions. Okay, the assumption that make the linear regression unbiased or strong. And then we will discuss how to check these assumptions. And then after that, so this is called a simple linear regression because we only have one explanatory variable. Okay. And then I think in day 4 or 5, I think we will talk about the linear regression with multiple explanatory variable or predictors. Okay. I think at the end of the week, if we have time, we'll talk a little bit about data management, which we haven't covered in week 1 and 2. Okay, so far we only use generate, EGEN. Oh, we haven't used EGEN yet. Okay, replace, generate, and filter so far. So there are several functions that you can use to during your data management session. So I think we would also talk about that if we have time. Yes, yes. Okay, so I think that is it today. If you have any questions, you can ask because we have some time now. Do you have any questions regarding this or regarding week 1 or week 2? Okay, I don't think any questions come up. Okay, that was so the question is how do we recode in R? Okay, that is what I'm talking about. Okay, if we have time, we'll talk about that in this week because linear regression. I'm thinking about day 4, day 5, and day 4, day 5 we will finish linear regression. I mean, along the way when we use when we are in R Studio, we will talk about it. okay? Because we have to deal with the data management in R again. And okay, so maybe I talk very fast. This is how you interpret the linear regression, okay? Wait, this is the slope, and this is the intercept. This is how you interpret the linear regression. Okay, it's okay. Okay, we are just recapping, and so if you have to leave, then just leave. It's okay. Okay, so how do we interpret the linear regression? It is quite similar to linear regression, but we give it a unit. Okay, in correlation, we say that if there is in correlation, we only talk about direction and magnitude. But here we quantify it. Okay, how do we quantify it? If we have one unit increase in high school graduate, okay, what is the unit here? It is the percentage point. Okay, so each percentage point increase in high school graduate, we will expect 0.62 percentage point increase in poverty line. Sorry, decrease in poverty line. Okay, because the relationship is negative association. Okay, do you get it? The idea? Okay, so this is how you interpret it. So if there is a positive association, then one unit increase in x, okay, x means the explanatory variable. One unit increase in explanatory variable, we will see an increase in a slope value, okay? It depends on a slope value. An increase in a slope value by response variable, okay? So always interpret in a context or explanatory variable, and always there will be a one unit increase in explanatory variable, okay? And then whether it is increase or decrease depends on a direction of the relationship, okay? And so if it is minus, then it will decrease in response variable. If it is positive, it will increase in the response variable. Okay, any other questions? Okay, I think that's it, right? So let's see everyone. See you.